Hey everybody, it's Mrs. Harbin, and we're going to do video notes 8A and 8B. So we're going to look at changes and models of chemical reactions. So here's a chemical reaction, here's a chemical reaction, and then we're going to look at signs and what it means. So make sure that you can do these. These are the goals for what we're learning. So make sure you read them. You could write them down. Remember, they'll show up on practices, they'll show up on the celebration, and when we're getting ready to celebrate. Okay, here's 8B. Some of these things you might already know how to do, and so you would just be able to do those. All right, so we talked about this in class, but a physical property is something you can describe about matter without changing its identity. So you can describe the size of something, and it still stays the same substance. You can describe its color and its shape. Chemical properties describe how substances react with other substances, and then they change their identity. So to decide if something's flammable, you have to change it, and then you know it's flammable. Okay. Changes can be physical or chemical. So physical change does not change the identity of a substance, right? So cutting this green stuff into pieces, it's changing it, but it's still the green stuff. We didn't change its identity, okay? The Statue of Liberty, when it was first given to the United States and finished, it was made out of copper, and so it was shiny copper color. But then over time, it chemically changed. So we found out that copper is chemically reactive with oxygen, and it made this new chemical compound on it. Okay, so a chemical change does change the chemical identity of a substance. So it's not copper shiny metal, it's a compound of copper which has a different identity. Okay. So what are some signs of chemical change? Well, you get an unexpected color change. So when you put Kool-Aid into water, the water turns red. That's not unexpected. So that's physical. But if you put, like we did in the lab, we put an iron nail into a copper chloride solution and a pink solid started to form or brown solid started to form, that's unexpected. So these are signs that something is changing chemically. And evidence of a chemical change means that the substance is changing identity. It is not what it used to be. It totally changes identity. And these are 5 things that you can look for. So chemical changes change identities because they rearrange atoms and bonds. Okay. So this substance is called nitrogen. It's got 2 atoms of nitrogen bonded together. This is called hydrogen, 2 atoms of hydrogen bonded together. And then it chemically changes. So this bond has to break. These bonds have to break. And then they rearrange so that you get this new substance, which is called NH3, and that's called ammonia. So that's a chemical change. And this is what's happening on the particle level. What would you see on the macroscopic level? Well, we see nitrogen gas. This is a gas. And hydrogen, which is a gas. But then when we're done, we have the substance called ammonia or nitrogen trihydride. And it smells really strong, and we use it for cleaning. And it is definitely not nitrogen. And it's definitely not hydrogen. It's a chemical new substance. Okay, so new substance. New substance. So what do we see? What do we see? We see 2 clear gases react, and then we see a new gas that has a really strong odor. So that's a new substance that forms. But look, 2 green atoms, 1, 2, 3, 4, 5, 6 tan atoms, 1, 2, 3, 4, 5, 6 atoms. So then notice the number of total atoms is constant. But this is 1 molecule, and these are 3 molecules, and this is 2 molecules. So the number of molecules can change, but we have to be able to find all the atoms. Okay, so the total number of particles can change, but the number of atoms can't. Now, this changes color a little bit, but over here I have 1, 2, 3, 4, 5, 6, 7, 8, 8 iron atoms. And look, it's a solid, it's a metal. Okay, oh, and here I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 chlorine atoms total. But it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 of those. So when we're done, okay, so these ones, they didn't change color, but they're showing up here in red. So I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then let's see chlorines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We can find them all. I know they look blue over here and they're green over here. So on a microscopic level, these bonds are breaking apart. Break, 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 break. break, 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 break. And then they come together differently and form new bonds. So this has totally different properties. This is not chlorine gas, right? It's a solid. It's got different atoms built into it. And this is a solid, but it was just iron atoms. This is a solid. This is an ionic compound. And this was a covalently bonded stuff. Okay. So we would be able to balance this equation by using coefficients. So I have an iron over here. I have iron over there. I have 2 chlorines and 3 chlorines. But if I put a 2 there and a 3 there and a 2 there, then let's see, for every 2 of these, I take 3 of these, and I get 2 of these. So 1, 2. All right, so 1, 2 of those, 2 of those, and 2 of those, 2 of those, 1, 2, and 1, 2. Okay. So this is a balanced equation, and it just works in those ratios to make stuff. All right, so chemical equations show the overall process. So these all break, 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 and then they reform into carbon dioxide and water. And then these numbers in front tell us how many of each thing. Okay, so here we go again. These bonds all have to break, and then new bonds form, and then we got to count the particles. All right, so you got to save atoms. Atoms will be saved. So here's 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total reds, but they're all in the form of O2. All right, and this is in the form of CH4. Then all of those bonds breaks, and we get CO2s. Here's a CO2, and then H2O. All right, so let's see if it worked the right way. So it says for every one of these, we're going to need 2 of those to get 1 of these and 2 of those. All right, so 1 of these, okay, and 1, 2 of those gives me 1 of these and 1, 2 of those. So 1, 2, 3, 4, 1, 2, 3, 4, and 1 black, 4 white, 1, 2, 3, 4 white. All right, so every one of these takes 2 of those to get 2 of these and 1 of those. All right, one of these takes 2 of those to get 1 of these and 2 of those. So this is what's happening. So these are ratios, and if we double this, then we got to double that, double that, double that. Okay, so then that's one way to balance it. So you can balance an equation by drawing the particles. You can also balance the equation by doing a list of atoms. Okay, so C's. I got 1 C on this side and 1 C on that side. H's. 4 H's on that side, 2 H's on that side. O's. 2 O's on that side, 3 O's on that side. Not balanced. So let's see, let's say I need some H's over here. So I put a 2 there. Now I have 4 H's on this side. I have 2 plus 2 is 4 O's. Still 1 C. Now it's still not balanced. So I go back to this side and say, all right, well, I need some more oxygen. So I put a 2 there. And then I cross that off and then 4. And now look, 1 of each, 4 of each, 4 of each. Yay. So you can balance an equation by drawing particle pictures. You could also balance an equation by doing this list them out. Okay. Another way to do it is just go back and forth until when you count them, you have all the same things. Okay, so what's a chemical equation? Is a sentence that describes what's happening. The stuff on the left is reactants. The stuff on the right is products. And this arrow means produces or yields. Okay, and then these are coefficients that are in front. And these are the chemical substances that react in that form. Okay, so here's propane, C3H8, oxygen gas, carbon dioxide, water, heat, and light, and so we can balance it by counting particles and drawing pictures, or we could list C's, H's, and O's down the middle and count them. Okay, so again, signs of chemical change. I know we're repeating this, okay? Heating or releasing or absorbing heat, changing color when gases are produced, and when precipitates form. Those are ways like, oh, this must have been a chemical change because you do not expect green stuff on bread. So that's mold, that's a chemical change. All right, ew, who's eating that toast? Not me. All right, smoke, heat, fire, those are all signs of chemical change. All right, so the coefficients tell you the number of particles and the number of moles. So this is not balanced, right? So we can draw particles and see how many we need to balance it, or we can do C's, H's, and O's. All right, so we have 1 on that side, 1 on that side, H's, 4 on that side, 2 on that side, and O's, 3 on that side, and 3 on that side. So it looks kind of balanced, all right? But if we count these particles, we can see that we're going to need some more H's on this side. So if I put a 2 here, that's going to make 4 H's. But then I have 2 oxygen and 4 oxygen. All right, so that's still not balanced. All right, so then I got to go back to the other side and try to get to balance. But my O's aren't going to balance because I have 3 and then I have 4 over here. All right, so I got to do something to get the oxygens to balance. So if I put a 2 here, that'll give me 2 C's. 4 plus 4 times 2 is 8 hydrogen. Okay. And then now I have 2 plus 2 is 4 oxygen on that side. So now the oxygens are balanced. All right. But then on this side, I don't have enough hydrogen. So I got to change this 4. I mean, it was a 2. I got to change it to a 4 to get 8 hydrogens. 8 hydrogens. And I have 4 plus 2 is 6 oxygen. But I also only have 1 carbon, so I need another carbon. So now I have 2 carbons. And then 4 and 4. 4 and 4 is 8 oxygens. But I don't have 8 oxygens over here. I have 2 plus 2 is 4. So if I put a 3 here, that'll give me 6 plus 2 is 8. Now it's balanced because my numbers add up. Now I could count here too. 1, 2 of the CH, 3 OHs, 3 of the O2s, 2 of those, and 4 of those. And look what happens. You can account it that way. You could account it this way. 1, 2 of these whole things. 1, 2, 3 of these whole things. 2 of the carbon dioxides and 4 of the waters, and it's balanced because we have 1, 2, 3, 4, 5, 6, 7, 8 reds. 1, 2, 3, 4, 5, 6, 7, 8 reds. Yeah. 1, 2, 3, 4, 5, 6, 7, 8 whites. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And then 1, 2 carbons, 1, 2 carbons. Yes, it's balanced. So we balanced it with particles and we balanced it with counting and making a list. Okay. So here's what you have to be able to do. You have to be able to relate what you see in the lab to what's going on in the chemical reaction. Okay, so what you see to what is happening to particles, happens to particles. All right. And then you have to be able to inspect the chemical equation and make sure the total net number of atoms doesn't change, which you're going to have to put coefficients in. You could draw pictures, you could write symbols, and when you're done, you have to have the same number of atoms on both sides. Okay, so to review, chemical reactions rearrange atoms and break and form bonds. That's what's happening microscopically. So what do we see? We see precipitates or heat or color changes, that kind of stuff macroscopically. We balance equations with pictures or lists or guessing and checking, and we make sure that we have all the same atoms that came in are coming out. And that's it.